Okay, cool. So again, some of the stuff that we're going to go through today, probably going to be review for many of you, but again, want to make sure we're strong on our basics, and it's never bad to go through and just reorient yourself to some of this stuff. Talking about normal distributions, z-tables, probability, confidence levels. Going to talk about standardized, transforming things to standardized scores, what we can derive from standardized scores, how we get probabilities, and then talking about interval estimates stuff. I'm going to beat you over the head with confidence intervals for this entire year. Hopefully pushing you to a point where so you see this as normal and wanting to incorporate interval estimates to most of your stuff, just because they contain much more information than just point estimates of stuff that we often see in our research. So last week talked about how having mean standard deviation starts to give us useful information about how large a score might be relative to other people in the distribution. But the problem is, if I just give you a raw score, you're stuck with limited information about sort of where that score falls relative to everybody else. Hey, I can give you a mean and a standard deviation, but still you have to do some mental calculations to try and figure out, is this a big score, is it a small score? And so what we can do is we can use standardized scores, okay? Standardized scores give us a common metric that's going to tell us information about the mean. It's going to tell us information about the standard deviation. It's going to tell you information about the rank of a given score, all within a single value, okay? And so what we can do with these z-scores, instead of saying, oh, Nick, I got a score of 103 on this thing. I'll be like, well, that's good. I don't know what that means, right? But if I tell you what my standardized score is on whatever scale it is, that gives you a sense for my rank position relative to other people who've taken that or completed that measure. And also, we can start to get into determining the probability of someone achieving a score that based on the distribution that we've got. So, best example of standardized distribution, something that's following a normal curve, probably IQ scores, right? IQ scores, these are cognitive achievement tests that have been normed to have a mean of 0, a standard deviation of 15, right? We know that intellectual ability falls roughly on a normal curve in the population, and so what we can do is we can say, all right, here's our normal curve, here's the average score, and then we've got standard deviations in the population equal to 15, right? And so your IQ score that you would get is a form of standardized score, okay? But this IQ score is going to be different than a z-score. If we're talking about a z-score, this is a distribution where we don't have, here we've got a mean of 100 and a standard deviation of 15. Standardized score, z-score is going to have a mean of 0 and a standard deviation of 1, okay? Doesn't matter what we're measuring, if we're turning that distribution into a z-score, mean is always going to be 0, standard deviation is always going to be 1. This mean and standard deviation defining features of this standardized distribution. We're going to have all sorts of different types of standardized distributions. If we're talking about a z-distribution, mean is always 0, standard deviation is always 1. Okay. Things that communicate essential information based on the score, value. All right, this is important once you get, because this starts to get into interpreting effect sizes. A z-score is literally telling you how many standard deviation units away this score is from the mean of the distribution. It's literally the number of standard deviations, okay? This is going to be important when we start talking about effect sizes, things along the metric of Cohen's d, right? Cohen's d is the same thing. It's just telling you how many standard deviations difference it is, or above or below. So start getting this into your head. Z-score, a standardized score, literally telling you the number of standard deviations from the mean that this score is, okay? And then we're looking at the sign. Sign plus or minus is going to give you the position. Are we talking how many standard deviations units above, how many standard deviation units below? This together in a very efficient package is giving us a lot of information about how a given score in a distribution ranks relative to everybody else. Okay? So if we're saying here's our z distribution, it's a nice normal distribution, it's a population of scores. Z of 1, we're right here, right? Well, how many standard deviations above the mean is this if it was Z-score of 1? 1, right? It's a pretty straightforward situation, right? Standard Z-score of negative 0.5. Amanda, what's a Z-score of negative 0.5 tell us?
And it's 0.5 below.
Yeah,
the mean.
half standard deviation below the mean, right? Z-score of 2.5 up here, right? 2.5 standard deviations above the mean, negative 1 a standard deviation below the mean. Very easily and efficiently, very straightforward, telling us how many standard deviations away from the mean an individual score is. Okay? And this is all probably review. Anybody have questions about Z-scores or position, things along those lines? Okay. So transforming our raw scores to Z-scores is our Z-score formula. Simple ratio. We're taking our score, we're subtracting whatever the population mean is, and we're dividing it by standard deviation. And we're using population symbols here. You can use it for sample distributions and things along those lines. You say basically we're taking the score, subtracting the mean, dividing it by the standard deviation. Okay. So if we say have a distribution with a mean of 10 and a standard deviation of 2, okay? And I want to find a z-score for x equals 12. What is my z-score, Kate, for this? Okay. So we got x is 2, mean is 10, standard deviation is 2. What's our z-score for x is 12. 1, right? We say 12 minus 10 is 2, divided by 2, we've got a z-score of 1. Okay, Emilio, what does that tell us about this person who scored x equals 12?
He's 1 standard deviation.
1 standard deviation above the mean, right? Same thing, Emilio, jump in. What if we have x equals 8? What's the z-score for that?
-1.
-1, right? So we've got someone who's a standard deviation below the mean. X equal 11. John or Nick, you want to handle this one?
0.5 above.
0.5 above, right? So you can start to see here very quickly and easily how this is going through. And now all of a sudden, right, I've got x equals 11. Well, I don't know, is that good or bad? I don't know, right? But if you tell me I've got a z-score of 0.5, well, okay. Now all of a sudden, I've got a sense for where this person is scored, okay? What if someone with a pen and paper or something, z-score corresponding z-score for x equals 17, if mean is 34.6, and standard deviation 8.2. Amanda, I see you type in there, thank you. What do we get for that one?
-2.15.
-2.15, exactly, right? And we're saying that this person is a little over 2 standard deviations below the mean based on this score, okay? So this is easy, simple, kind of straightforward way of standardizing a raw score into a metric that gives us much more information than the individual score on its own, okay? So again, if we're thinking about any type of standardization, whether it's test statistics, effect sizes, things along these lines, always follows this ratio, okay? And as I talked about in the last lecture, understanding this, so what happens to, say I've scored 5 points above the mean, right? What happens to my z-score, Evelyn, as my standard deviation goes up or down, right? So I've scored 5 points above the mean, right? And I really hope that 5 points above the mean means I'm super smarter than everybody else. Am I hoping for a big standard deviation of this distribution or a small standard deviation?
Small.
Small, why is that?
Because that means that you're above the mean.
Right. Just looking at this ratio, as this standard deviation goes up, right? If we're holding this constant, that means my z-score is shrinking down and down. We're dividing a number by a bigger number, it's going to be smaller. As this standard deviation goes smaller and smaller, as deviation gets less and less, that's making that score a little higher and higher. So this is the same thing. This is going to be the same thing that comes up with test statistics. except down here in the denominator, we're going to be talking about standard error, right? Standard error is almost always in the denominator of your test statistic ratio. When we have big standard errors, what happens to our test statistic? It goes down, right? Generally, we don't want small test statistics. We want small standard errors. We're dividing something by a smaller number, makes our test statistic go up. Understanding this math and understanding how all this stuff works out going to be important is just a general concept moving forward. Questions on this? All right, so one of the things for this set that you're going to do is going to be incredibly helpful for graphing some of this stuff out. You might think, oh, graphing's for babies. It's not. It's for graduate students too. It'll help you from getting confused and turned around in this stuff. So here we have our normal distribution, right? And our z-scores here, 0 is the mean, 1, 2, 3 standard deviations. Here, if our raw distribution has a mean of 34.6, with a standard deviation of 8.2, our raw score of 17 is going to be a little over 2 standard deviations below the mean here, right? And what we can do if we wanted to is run this raw score out here. So we've got a mean of 34.6, 1 standard deviation, 42.8, 2, 56, same thing going back. This can be a nice way to go through and organize where scores are falling on these distributions. Yeah?
You can't, this is a question, but you probably can't do this if the original raw scores aren't normally distributed, right?
You don't tell me what I can do or can't do. You can do this, yes, okay.
Okay.
Yeah, you can create z-scores, you can have your z-distribution do this however you want, but it's important to remember we're going to talk about this. Just because you've created the z-scores doesn't mean you've got a normal distribution, okay? And this is where, when we start to get into probabilities, and if something follows a known distribution, then we can start using existing documentation to determine probabilities. If we don't know what the distribution of a set of scores is, then we start getting into some problems, and this is what happens when we violate test statistics, right? When we look at our test statistics, if I have a normal t distribution, right, and I've met all the assumptions of my test, then I know with an infinite number of replications that if I do this over and over again, and if the actual sort of difference between sample 1 and sample 2 is 0, and all of my stuff is normal, and my variance is equal across my two groups, that my t-statistic is going to have a distribution like this, right? If the null hypothesis is true, right? But if I start to violate assumptions, right, then the sampling distribution of that t-statistic isn't the one we all know and love. It's something different, and I don't know what it is. And then that starts to have implications for making inferences about whether or not I have sufficient evidence to reject the null hypothesis or not. So we'll get into that when we get into hypothesis testing stuff. But just because I can z-score whatever I want, and that tells me how far away in terms of units of standard deviation. But if I want to start making strong inferences about how likely or unlikely those scores are, then that starts to get a little bit tricky.
So doing that is still useful in figuring out certain things about the distribution of the data.
Yeah.
And seeing if it's skewed or
Mm-hmm.
something
Yeah.
like that.
And so all of this stuff, you all will get all sorts of fun experiences of going through and screening data and looking at a number of different directions to start to make, say, what conclusions can we draw from this data, and then sort of how we move forward with stuff. All right. So z-score formula, but if we go back through to 6th grade, do you start algebra in 6th grade? What grade do you start algebra with? You guys are younger than me.
Yeah.
8th grade? Okay. 8th grade algebra. What we can do, this is a simple algebraic formula. We can start going through and transform this around to start solving for different components of things, right? So for example, we could say, what's the raw score for, if I got a z-score of 1.96, mean of 73.6, and a standard deviation of 14.8, okay? So just as a refresher, so we got z equals x minus my mean over here, right? But what I really want to know is I want to know the raw score, right? I want to know x. So what we can do is we can just kind of work backwards and start solving this equation for x. So you remember, I can get that standard deviation out of the denominator by multiplying both sides by that, so I get rid of that. And then I've got standard deviation z equals x minus the mean, right? Subtract the mean off of that, and then subtract the mean over here. It's going to give me x equals, adding, sorry about that, is going to be mean z plus, the mean, okay? So with that, what I can do is I can say, okay, well, I can say x equals 73, standard deviation is going to be 14.8, my z-score 1.96, plus 73.61, did I get that right? 3.6. Okay. And what's my x here?
102.
Yeah, so we'll say 102.61. Okay. Generally, with these z-scores, take your z-scores to 2 decimal places, just for whatever imaginary precision I think we have here, right? Okay, but do you see people see how we're just using basic algebra to go back through and sort of calculate this? Okay. Questions on this? So what happens then? Let's say if we've got, we've got a population with mean of 65, a raw score of 59 corresponds to a z-score of -2, right? And we don't know the standard deviation. Okay, so we know that, again, z is going to be equal to x minus mu over this, right? And now what we want to know is we want to know the standard deviation. So we're going to solve for standard deviation. Again, multiply standard deviation here. That goes away. Which gives us standard deviation z equals x minus mu, right? And divide by z, which gives us our standard deviation is x minus the mean over z. Okay. So here we can say standard deviation is going to equal 59, right? Yeah. Minus 65 over -2. What do we get? 3, right? And one of the important things to think about as you're going through and doing this, remember, always, always, always check the plausibility of your answer, right? So this first one, I know I've got a z-score of about 2, right? And so I'm saying if the mean is 73.6, and I'm seeing my raw score, it corresponds to 102.6. Is that a plausible answer? Yeah, right? It's 102 is about 2 standard deviations above, so that all kind of fits, right? Here with this second one, right? I'm saying I've got a mean of 65, population mean of 65, and a score of 59. What does that automatically tell me my z-score needs to be? Oh, well, it is negative, okay. But then going through, if I go through and sort of work this out and retransform, right, is this a reasonable answer or a reasonable value? Well, if I take 59 minus 65 and divide it by 3, do I get a z-score of -2? So working backwards and making sure that the stuff that I'm actually calculating makes sense if I work backwards with this. Okay. All right. Just to do one more. So we've got a population with a standard deviation of 4, x is 33, z-score of 1.5, look for the population mean, right? But what I'm looking for is I want to get mu, right? So I'm going to multiply here, cancel that out. Let's add mu. Add mu here. So we get here plus equals x, right? And we just subtract this, we get mu equals x minus here. Is that right? Yep, should be. So here, we got mu equals, in this case, we've got a score of 33 minus standard deviation of 4, z-score of 1.5. What's our population mean? 27. Okay. So again, if I'm being honest, rarely in your lifetime will you have to go through and calculate z-scores by hand and go through and do this type of stuff in actual practice, right? We don't have to do that anymore because we have computers that go through and run all this stuff. But one, it's important because you now know, so I want you to know what's going on, the nuts and bolts in the background with this. Other thing too, if you're handy with your algebra and can run backwards with stuff like this, it makes it it's a nice thing for going through and being able to check on things that you might want to know about published research if they don't provide this stuff for you, right? If I know what the formula is for an effect size, and I don't know what they've used as a standardizer because I'm suspicious that maybe they've chosen the smallest variance estimate possible to make their effect sizes real big, I can take the information that they've got and work backwards and figure out what their standard deviation, what they're using as a standardizer, and that's very, very helpful, right? Because I can go through and say, okay, well, or maybe they've given me a standard error estimate, but I want to know what the standard deviation is. I know how standard error is calculated. It's basically a ratio like this. You can work backwards and get the standard deviation for some existing data that they haven't already gone through and reported. If you know this and can work flexibly with these formulas, it's incredibly helpful for going through and figuring out information that you need for power analyses, doing some double checks on people's interpretations and assumptions and things along those lines. It just makes you really handy in being able to go through if you know how these things are calculated and then can work backwards and get various components if those are of interest to you for some reason. Okay. So, yeah, flashback to middle school algebra, but people feeling comfortable with just this general process. Okay, cool. So, again, why we're doing all of this is our z-score is giving us an exact location of an x value within our distribution, okay? And what we can do is we can start comparing. If we know a z-score, we can start comparing relative to position regardless of whether or not I'm looking at different things with different mean, standard deviations, things along those lines, okay? So let's say Henry's participating in study personality, scores an 87 on a measure of conscientiousness, 73 on a measure of extroversion. Which personality trait is more prominent for Henry? What do you think, Layla?
Sorry, what was your question?
So which would you see? You got an 87 on a measure of conscientiousness, 73 on a measure of extroversion. Which personality trait is more prominent?
Conscientiousness.
Maybe. Do we have enough information to make that determination? We don't know, right? Because who knows, maybe this measure of conscientiousness is on a scale from 50 to 100, and this one is on a scale of 60 to 250. I don't know why that would be, but we do weird things with our scaling, right? I don't know, I can't tell. But if we transfer these into z-scores, now can I tell? Yeah, I can say, well, he scores a standard deviation above the mean in conscientiousness, but 1.5 standard deviations above the mean on extroversion, so it looks like for him, relative to everybody else, the conscientiousness is more of a dominant. He's scoring higher on this than something else. Here's an example. I'm Claire. I'm just going to disclose that right now. Interested in creating a composite quality of life variable based on 3 different measures. How might I do this, right? Well, if I'm doing it the right way, I would probably get into some SEM and model a latent construct of quality of life. But let's say I'm a second year student, I'm not to that level yet, right? What I could do, if I've got three quality of life measures, what I might do is just calculate z-scores and use those z-scores to create a composite measure, right? Because if one of them's on a scale of 0 to 100, another one's on a scale of 20 to 60, and another one's on a scale of -6 to +6, I can't just add them all up, right? That doesn't make any sense. But if I go through and I calculate z-scores, then I can go through and aggregate those and say, well, and hopefully there's correlations between these measures if they're all measuring the same thing, right? What I can do is use those z-scores to create some sort of composite measure that's representing where this person falls relative to other people in the distribution to get something a little bit more useful. Okay. Questions on this? So, okay, and so this literally gets into the issue you were talking about, right? It's thinking about our distribution of z-scores. To this point, we've been talking about z-scores as having this nice bell-shaped curve, right, which we're all pretty excited about. But, which it's important to recognize, and this sometimes gets away from people, just because I convert a set of scores to a set of z-scores doesn't mean that I have a normal distribution of anything, right? All I've done is I've taken this distribution, this raw distribution, and rescaled it so that it has a mean of 0, standard deviation of 1. So, distribution of z-score is going to have following properties. Shape of the z-distribution is going to be identical to the shape of the raw scores. Changing everything to a z-score isn't going to change the shape of your distribution. It's going to be identical to your raw distribution. But if I do this correctly, the mean of my z-distribution is always going to be 0. Standard deviation of the distribution is always going to be 1. And again, if we go through and in a set of scores, transform all of those into z-scores, we're going to have a standardized distribution that's going to have a set mean, a set standard deviation. And if we're talking about z-scores, that set mean is 0, standard deviation is going to be 1. So let's say we've got a set of raw scores. Simple example, 1, 6, 5, 2, and 3, 2, 3, and 2, right? So if we take the mean of this distribution, it's going to be 3. Standard deviation of this distribution is 2. So if I go through and I say, here are my raw scores, my score of 0, right? This is going to be a standard 1.5 standard deviations below the mean, right? Because my mean is 3, my score is 0. That's 1.5 standard deviations below the mean. Z-score 1.5, negative 1.5, right? These are pretty easy and straightforward. You can kind of do these in your head, but you can also go through and scratch them out with using your z-score formula. They'll work out, right? Score of 6, right? Score of 6, if my mean is 3, score of 6 is a standard deviation and a half above the mean, right? I'm going to have a z-score of 1.5. My raw score of 5 is going to be 1 standard deviation above the mean, right? So 3 plus 2, if I've got a standard deviation above, that gets me to 5. Standard deviation above, score of 2, it's going to be a half standard deviation below the mean. Score of 3 is going to be equal to the mean, right? So I'm going to have z-score 0 there. And then once again, our score of 2 is a half standard deviation below the mean. But if I go through and I add up and take the average of negative 1.5, 1.5, 1, negative 0.5, 0, and 0.5, negative 0.5, if I take the average of that, what am I going to get? Is 0, right? Because it has to be if I've done it correctly, right? And if I were to calculate standard deviation there, my standard deviation would be 1. You can kind of see how we kind of work through this in our head, and again, if you wanted to, just to make sure that you're on the same page, you could go through and run all these out by hand. But again, a nice shortcut for this is think about how many standard deviations above or below the mean. Here we're working with easy whole numbers, and it kind of works out nicely. So if I go through though and take create a histogram of my raw scores, and I create a histogram of my z-scores, How do these two relate to one another, Nick?
They're the same.
They're the same, right? Changing everything to a z-score didn't change the shape of my distribution. My z distribution is no more normal than my raw distribution. I just rescaled everything, right? But you notice, whoops, that my mean here is, what was it, 3? Is that right? Mean here is somewhere around here. Mean here is going to be 0. Everything stays the same. All we've done is just rescale it in a way that's going to communicate more information to me than just throwing out raw scores. So if you think about this, you think about IQ tests, right? Does the sum of all the points you can get on an IQ test equal sort of the max score you can get on an IQ test? No, right? The average number of actual points you score isn't 100, but we just rescale those raw scores to a distribution that has a mean of 100, standard deviation of 15, right? Same thing with this. Doesn't change the shape, doesn't change the properties. You're just transforming these scores into something that communicates more information, is more useful than just telling me raw scores. So other standardized distributions, T-scores, right? Anybody done, I can't remember, so no one's done, has anybody done personality testing? Sometimes personality tests. MMPI stuff uses T-scores. Not anything special or new terribly, just a distribution, standardized distribution has a mean of 50, and mean of 50 standardized standard deviation of 10. IQ scores, mean of 100, standard deviation of 15. SAT scores, right? People are familiar with this. Mean of 500, standard deviation of 100, right? If I add up all the points of everybody's SAT exams, the average isn't going to be 500 points, it's going to be some other number, right? But for the purposes of communicating people's scores relative to other stuff, mean is set at arbitrarily at 500, standard deviation of 100. And so when we go through, and we want to go through, transform into some other type of standardized distribution, the first thing you're still going to do is go back through and first transform your raw scores to z-scores, and then transform those z-scores into new standardized scores with a specific mean and standard deviation, right? So if have a distribution, right? And for some reason I want this distribution to have a mean of 20 and a standard deviation of 5, right? I'm not going to take my raw scores and immediately transfer them into this distribution. What I'm going to take is I'm going to take my raw scores, translate those into z-scores, and then can go through and take those z-scores and transform those into whatever distribution, standardized distribution I want to create here. Okay. So let's say we've got a set of exam scores. We want to have these standardized to have a mean of 500, standard deviation of 100. Okay. And let's say these are scores on a exam that I gave in my intro psych class, right? But I want to be fancy and put them on a standardized score on a standardized scale that's equal to SAT scores because I've got too much time on my hands or something. Okay. And so what we're going to do, distribution of our raw exam scores has a mean of 57, standard deviation of 14, and we're going to do calculating standardized scores for the following raw scores. So the mean of these isn't 57, the standard deviation of these isn't 14. That's kind of the bigger distribution of exam scores. But what I want is I want standardized scores for these 4 exams from a standardized distribution with a mean of 500, standard deviation of 100, with mean of the raw scores being 57 and 14. So what I'm going to do, again, and this is how I would recommend you lay this out. So here are my raw scores, right? So I pulled 4 exams. Mean is 57, standard deviation is 14. Okay. And so what I'm going to do is I'm going to take my raw score of 64, and I'm going to say, okay, my raw score of 64 is a half a standard deviation above the mean, right? So I take 57, or 64 minus 57, I get 7, right? That's a half standard deviation if my standard deviation is 14. So this is a half standard deviation, so my z-score is 0.5. But if I want to transform this into a standardized distribution with mean 500, standard deviation of 100, well, I just add half of 100 to my mean here, and so my new standardized score is 550. people see how I did this and the logic behind this? Yeah, okay. So I've got a score, raw score of 64, right? And I know my the mean and standard deviation of the scores that I collected is 57 and 14, right? So if I take 64, create a z-score of this, I get z-score of 0.5, right? But for my new standardization, what this is telling me is what I'm going to do is this score is half a standard deviation above the mean, okay? And so if I want the mean of my distribution to be 500, and this score is half a standard deviation above the mean, then I just take whatever I want my standard deviation to be, multiply it by this, and then add it to my new distribution here, okay? You see that? Okay. Same thing. What's that?
No.
Okay, so same thing. So I've got a score of 43. This is a standard deviation below the mean. If I take 57, or excuse me, 43 minus 57 divided by 14, I get -1, right? So that's my z-score. So I know that this score is 1 standard deviation below the mean. So if I want my final distribution, my re-standardized score to have a mean of 500, standard deviation 100, then I take 500, it's a standard deviation below, I subtract 100 from that score, and I get a new score of 400 here. Okay. Same thing, 57, this is equal to the mean, gives me a z-score of 0. Well, I take 0, multiply it by 100 is 0, add that to 500, then it's just 500. Same thing, 71, this is standard deviation above the mean. If I take 71 minus 57, that gives me 14. 14 divided by 14 is, or 14 divided by 14 is 1, right? So then I've just got 1 standard deviation above the mean. So I've just got 1 standard deviation is 100. Add that to my mean is 600. And now what I've got is a new standardized scale, right? That I've derived. This is my raw scale. This is my z-scores. And this is my new standardization, okay? And so again, if we just think about z-scores as telling me how many standard deviation units above or below the mean I'm working with, all this starts to fall into place pretty quickly. Questions on how we went through and sort of made this transition across these? All right, and this is where some of this graphing stuff can start to become helpful, right? So here is always start out with your z-scores, right? Because that's easy, you know where those things are. This is 0, 1, 2, -1, 2, right? But then we can go down here and I can number line my raw scores. So I know my mean is 57. 1 standard deviation below is going to be 43, because if I take 57 minus 14, it's going to be 43. 2 standard deviations below, 29. Same thing, 1 above is going to be 71. 2 above is 85, right? And now down here I can start laying out my new standardized scale. I know I want my standardized scale to be 500. Why? It's because I felt like it, right? This can be whatever you want. Your standard deviation can be whatever you want, right? Standard deviation can't be negative, but it probably shouldn't be 0. But anything above that, right? But we can go through and start saying, all right, these are the scores that are going to correspond to these different levels. So it gives you a great amount of flexibility. And if you're doing anything with measurement or testing or things along those lines, it's going to be important to be able to move back and forth through different types of standardizations to provide some flexibility, make sure that you're consistent with other types of scorings and things along these lines. Okay. Questions with this? Okay. Again, at the end of the day, it's pretty simple, basic algebra types of stuff, but if your algebra muscles are rusty, which I imagine they are, sort of this is kind of where this is going to take. Like, when am I ever going to use algebra? Today, right? So, hooray for 8th grade math. All right. So the question is, why is this important, right? Why would we do this otherwise than just kind of something to do, right? One, allows us to compare different scores irrespective of the shape of a distribution and the characteristics of distribution, right? If I go through and I standardize, if I say, so well, on this exam, one person got a 38 and another person got a 47, right? How much different are those scores? Well, I don't know, it's hard to tell, right? But if you give me those in z-scores, regardless of what the distribution is, it tells me how far apart or how different these scores are going to be from one another, right? And so in general, for any type, with some score or some type of measurement that falls along some sort of known or assumed distribution, what we can start to do is start to infer the probability of obtaining a given score based on known properties of that distribution, okay? And so what we can do is we can start saying, if we're working with known distributions, we can start to answer the question, what's the probability of randomly selecting a score greater than or equal to X, or less than or equal to X? Okay? And this is where our standardized Z table starts to come in. If we're assuming a normal distribution based on how many standard deviations out you are from the mean, we can start making very, very specific interpretations about the likelihood of obtaining a score of a certain level or higher, assuming that whatever we're measuring is following a standardized distribution. Okay? And again, this is something everybody's probably familiar with. We see that for a normal distribution, about 68, a little over 2/3, 68% of all the scores are going to fall within one standard deviation above or below. If we go out to 2 standard deviations, we're talking about 95%, 3 standard deviations, 99%, right? So if I'm looking at something, if I'm looking at an IQ score, right, and I know that IQ, intellectual ability, in theory falls along a normal curve, right? And I say that this person scored 2.5 standard deviations above the mean. Is that a likely event or is that an unlikely event?
Unlikely.
Very unlikely, right? So we're talking about something that's hanging out here in the upper 5%, right? If we get someone scoring above 3 standard deviations, that's an incredibly unlikely event, right? So we can start to make inferences about the likelihood of someone randomly selecting someone with a score that level or higher, right? Evelina, what if we say someone scored half a standard deviation below the mean? Is that a likely event or an unlikely event? A likely event, right? Because that's kind of in the body, right? We're expecting most people kind of fall between there, right? So it's a little less, right? But it's kind of what we would expect. But as we start to get out on the tails, and the reason that we can do this is because we have something that follows a known property of a normal curve. If we're thinking about our distributions and how our scores are playing out, and how we think about frequency as related to probability of event, anybody progress on to like Calc 2 types of stuff? Okay, right. So we're talking about integrals here, right? We're talking about areas under the curve. This is basically the mathematical sort of basis for almost all of our statistics, right? Because if we have areas that represent certain portions in our normal curve that are areas that are associated with certain probabilities, and because we know that proportions probabilities are equal, what we can do is we can start using sort of these curves to determine the likelihood or how likely or unlikely it is to start to select certain types of events. So if we go through and we say we have a population of scores, so these are all the scores in the universe for whatever this measure is. 1, 1, 2, 3, 3, 4, 4, 4, 5, and 6, right? And if this is the frequency distribution of my graph, right? And my question is, what's the probability of randomly selecting a score greater than 4, okay? Well, if I go through and these are all the events, and these are the 2 that are greater than 4, what's the probability of randomly selecting a score from this population that's greater than 4? You say, Haley? 20%, right? How did you do that?
There are 10 scores, and 2 of them are greater than 4.
Perfect, right? That's all that's going on with any of these distributions, okay? I mean, the math is more complicated, but in concept, this is exactly what we're talking about, right? We've got a total of 10 scores. 2 of those scores fall above 4, and so what I can say is the likelihood of randomly selecting a score that's greater than 4 within this distribution is about 20%. right? Is that likely or unlikely? Not particularly likely, right? If these are my odds at a casino game, I'm not super excited about that, unless I'm a fool. Those are out there, right? But I'm probably going to lose, right? Most of the time, right? Not all the time, but most of the time, that's not a good bet. It's not a terribly likely thing, but I shouldn't be shocked if it happens, right? So, within this same concept, right? We're thinking about a normal curve as documenting the frequency of some type of measure, something like that, some naturally occurring phenomena. Natural distribution is nice because a lot of things follow a natural distribution within the population. Things like height, mass, intelligence, things along these lines. This is a nice bell-shaped curve that we find a lot of things follow along, right? If we're talking about a normal curve, it's nice, it's a symmetrical distribution, right? Highest frequencies happening right there in the center. We see as scores get extreme to the high end and the low end, things start to taper off, and the mean, median, and mode of your normal distribution are all going to be identical here. Okay? And the nice thing is that people smarter than me have gone through and figured out exact probabilities associated with an infinite number of scores ranking along those along that along that bell-shaped curve. And the z-scores, these standardized scores, that provides a specific unit of measurement, right? That says at this score or above or below, what's the probability of obtaining the score greater than or equal to this, or less than or equal to this score. And so basically what this is doing is it's documenting, it's making a cut where we can start to determine sort of what the area under the curve at this point or over, right? If you wanted to get into sort of basic math of it. Luckily, we don't have to crank out integrals every time we do this because people have gone through and documented this in sort of nice table format so we can go through and calculate this, right? So in our previous example, we have a sample frequency. We've got 10 scores, right? And we want to know what the probability of randomly selecting a score of greater than 4. Well, we've got 10 blocks. We've got 2 blocks here. It's 20%. Right? If we take this into our normal curve, we can do the same thing functionally based on our tabled values here. Let's say I've got a mean of 34.2 and a mean of 6.8, right? What's the probability of randomly selecting a score greater than 45? Okay. I can go through and figure this out, assuming that whatever it is that I'm measuring is following this normal distribution. So we're thinking about probabilities under your normal curve. Again, this is your function of your normal curve. Isn't that beautiful? That's pretty cool, right? We want to get a tattoo of that. That would be. I'll give someone $5 if they get a tattoo of the normal curve. Okay, that's a true offer. So I'll give you a crisp 5 if you come in with that. But if we're going through and taking a look at our distribution here, if we have a normal distribution, again, 68.2% of this curve falls between -1 and 1. Okay, 95.44% is going to fall between -2 and 2 as we start to get farther out, increasingly more area under the curve, right? And so when we're out on the tail, when we're getting down through this very small amount of area underneath that tail, suggesting that we're working with events that occur at very low probabilities based on the overall distribution. Is this triggering memories people kind of sort of starting to get and remember kind of what's going on? So the thing is, in undergrad statistics, you kind of maybe touch on this in like 5 minutes and sort of just kind of go through and say, well, these are the things, and you just pull that and trust me, this is why it happens. Can't do that here just because this idea of distribution is such a central component of applied statistics, wanting you to understand kind of how this is all fitting together. Okay, questions, and don't be scared because people have questions. So you're keeping questions from me. I know it. Yeah.
How did you get the percentages?
Calculus. Okay.
Is that something beyond
Yes, I'm not asking you to do calculus. Yeah, no. We've got other things to do than to crank out integrals and things along those lines, right? But basically, sort of all the values here, these probabilities, these are just areas under the curve, right? And so based on a curve that follows this formula, they've done all the math for you, right? This is something that you can go ahead and trust that there's no new business that's been going on in the past 100 years in terms of determining areas under the curve here. Okay. But in general, knowing where some of these benchmarks are for a normal distribution starts to become important, just because they start to become handy for knowing sort of where certain cutoffs are. So let's say population of adults, heights normally distributed, with a mean of 68 inches, standard deviation of 6 inches. Okay, given probabilities of normal distribution, what's the probability of randomly selecting an individual at or taller than 80 inches? Right. So basically, what's the probability of randomly selecting someone who's 6'8" or taller? Just knowing what we know about humans, is this a likely event? No, right? And so already this should start to give you an idea of what you probably should turn up with this, right? So what we're going to do here, first thing we would do is sketch out our distribution, right? So we're saying, here's my distribution, normal distribution of height. Mean is 68, I know a standard deviation is 6, right? And so if I add 6 to 68, I get 74. That's one standard deviation, right? Well, what I'm looking at is randomly selecting an individual at or taller than 80 inches, okay? Where does 80 inches fall relative to my mean? Upper end, right? So we're gonna go down through and draw some line somewhere here and shade off, this is the area that I'm looking for. Okay. Then what I'm gonna do is I'm gonna identify the location of 80 by calculating a z-score for that. Okay. So if I go through and I calculate a z-score of 80, well, if my mean is 68, standard deviation is 6, 80 is 12 points above 68. It's going to be a standard z-score of 2, right? And we can calculate that if you don't want to do that in your head. You take 80 minus 68 divided by 6 is going to give you positive 2. So we've got a z-score of positive 2 here. And then what I can do is determine the probability associated with my area of interest using my unit normal table. Okay, and that's what I've given you here, right? Anybody not used a unit normal table before? Okay, so no new ground that we're breaking here. Basically, our unit normal table, it's kind of a headshot of it. What we can do is we can go down along the left column here. We have standardized scores going from 0 up to 3, and then we start, once you get above 3, it starts to not make a whole lot of difference one way or the other in what you're doing with stuff, right? But what we can do, and this is laid out nicely, is we can go through and find a certain score, and we can start to give a probability that's associated with the larger portion, smaller portion here. So if I go through and I say, if I have a z-score of 0.4, okay? And this is actually kind of nice. It'll be useful for some of the stuff that you're doing. Let's say I have a z-score of, I want to know the likelihood of obtaining a score that's at or greater than some score that's equal to a z of 0.4, okay? So my z-score is 0.4 that I've calculated. So I go through, find my z-score here, z-score of 0.4, right? And I say I want the smaller portion, so we've gone through, so this z is 0.4, I'm looking for this distribution. So this is the smaller portion. I go through, I say, you see it's 0.3446. So what I would say is that the probability of me randomly selecting a score that's 0.4 standard deviations above the mean or larger is about 35%. Okay. Now, if I wanted to say the larger portion, if my question was, what's the probability of me randomly selecting a score of z-score of 0.4 or lower, well, then that's going to be this body of the distribution, right? And so that's gonna be about 66%, 65.5%. Okay. So basically what we're doing the same thing as the block example, but now we're just using a continuous distribution. Calculating a z-score and assuming that whatever we're measuring falls in a normal distribution, we can start determining the probability of selecting scores at or above that certain level, okay? So in this example, right, we had a z-score of 2, okay? Someone tell me, using the unit normal table, what's the likelihood of randomly selecting someone who's 6'8" or larger? Oh, right there on the back.
2.3.
What's that?
2.3.
I'm sorry, one more time.
2.3%.
2.3%, and how did you get that?
Just went to the Z2, then went to the smaller portion, because that's the portion that the odd is, which is 0.0228.
Yeah,
which is
exactly, right?
0.2.
So we want to get really specific. The probability of me randomly selecting someone who's 6'8" or taller, given the information that we have, is 0.023, or about 2.3% probability, or if you want to look at a percent or probability, you don't have to put or percentage on it, right? Is that a likely or unlikely event? Probably not, right? So about 2 times out of 100 will I randomly select someone who's 6'8" or larger. Okay. People see where Emilio got that off of our Z table. Okay. So this starts to become important when you're graphing these out. Again, this can be deceptively tricky. So make sure that you are graphing these out and using this to go through and position. Make sure that you're on the right thing. What if you would have found that the likelihood was 0.6% or 0.60 of randomly selecting someone 6'8" or taller? What would be the problem with that? Yeah, I should be concerned because I know that we're not walking around with giants, right? Like that's, I was getting freaked out. Like I'm a tall guy. If someone's like my height or tall, it weirds me out because it's like, oh, it's Goliath, get out of here, you're scary, right? But it would be an odd thing, right? And so we should be able to look at that, if that's what our numbers are telling us, and say, well, that doesn't make sense because that's not sort of how real life works, right? So always go through and thinking about, are the things that I'm calculating making sense? Okay. All right, so if we run through these couple of examples, assuming a normal distribution, what's the probability of selecting a z-score at or greater than 1? What do you think, Amanda?
About 16%.
Close to 16%, right? I would call it 15.9, right, or 0.15. With these probabilities, carry probabilities out to 3 decimal places, I guess, for the purposes of this. That gives sort of sufficient precision there, right? But yeah, about 0.159 would be the probability there. Okay, people see where we got that? John, you're back there hiding from me. What's the probability of selecting a z-score at or less than 1.5?
The 0.933.
What's that?
0.933.
0.933, perfect. Why is it not 0.0668?
Because then you'd be selecting a score greater than.
Exactly, perfect. So always making sure we know, here we're looking at a score above, here we're looking at a score below, right? So we're looking at the bulk of that distribution. Right? All right. Nick, so assuming a normal distribution, what's the proportion of the normal distribution that's contained beyond, and by beyond I mean above, negative 0.5?
It would only be about 30%.
What's that?
About 30%.
Okay, so be careful here, right? And so this is where I'm tricking you, and I did that on purpose, right? So we're thinking about what proportion of the normal distribution is contained above negative 0.5. So if I go through and I sketch, here's this, right? Negative 0.5 is somewhere here, right? And I wanna know stuff above. Okay, so what am I looking for there?
Larger portion is.
The larger portion, right? And so I'm saying, how much of the population is gonna be above a standard deviation, right? And so what we wanna do, the nice thing about these Z-tables is, again, because the distribution is symmetrical, we can start going through, and this is where graphing things out start to become helpful, right? So what proportion of the normal distribution existing above negative 0.5? If I go through, I say negative 0.5 below the mean, I'm looking for the stuff above. That means what I'm going to do is be looking at the larger portion, and so looking from that angle. Okay, people kind of see sort of how that works out. And again, this is where graphing these out are going to be helpful with pulling this together. So pretty straightforward. Z-tables, pretty easy to use. Questions about going through and running some of these types of problems? Yeah.
So then for that last question, would it be 0.691?
Yes. Yep. So the probability is going to be 0.692, I guess, if we're rounding, right? Yeah, of randomly selecting a score that's greater than a standard deviation below the mean.
And would we typically report the probability as in this format or as?
Yeah, go ahead. And I mean, probability is probably more specific. So yeah, just go ahead and report probabilities for this assignment. I mean, I'm going to overload you guys, but so this will be assignment 3. I'll ask you to be doing some of these types of things. Just go ahead and report probability to like 3 decimal places. Okay. All right. What about for normal distribution? We're just flipping things around a little bit. Want to know what z-score separates the top 10% from the remainder of the distribution? Laura, do you want to take a stab at this one?
Yeah, I guess it's chart.
This is about 1.28.
Perfect. How did you get that?
I looked at the smaller portion and found at roughly where it gets 10%.
Yeah, right. So again, if I'm saying, all right, I want to know what z-score separates the top 10% of the rest of the distribution, I'm going to put this out and I'm going to say, okay, this I'm looking for about 0.10 here, right? What I can do is I can look down, and so this is going to be the smaller portion. I can look at my z-table and say, all right, where do I get closest to top 10%? Well, we've got somewhere between 1.28 and 1.29, right? But if I want to make sure I get the top 10%, if I go 1.28, or excuse me, 1.29, I'm going to get less than the top 10%, so my default is probably going to be 1.28. I get a little more than the top 10%, but not that much. Okay. People see how we got that? All right. How about this? What for normal distribution, what z-score form the boundaries that separate the middle 60% of the distribution? What do you think, Amanda? You want to take this one on? So again, this is where graphing things out starts to become useful, right? So here's my distribution. I want to know the scores. Get that middle 60%. How am I going to calculate that?
So is z-score of 0.25 shows a larger portion of 0.5987. So I think that would be your lower bound that would capture the larger portion.
Now what's the z-score here?
0.25.
Okay. All right, so now this one's going to be a little bit tricky, right? Because we want to get something that captures the center 60%. Anybody have an idea on how we might approach this? Yeah, Emilio.
We will take the mean to z proportion, so that far left column, and it does mean to it, so you take that by 2. So we probably want to do 0.84 as a z.
Yeah, yeah, okay. So think about it, remember, use the properties that this distribution is symmetrical. If I want to get the middle 60%, right? Well, I know that if I'm looking for the middle 60%, I'm going to have here's my middle. I'm going to have 30% on this side and 30% on this side. That's going to be giving me the 60, right? But because this distribution is symmetrical, what I can do, and this is a nice table because it'll give you from the mean to sort of whatever your z-score is. If I just look down that mean to z, and I find something that gets at that middle 30%, so this percent, it's about 0.84, right? And so from negative 0.84 to positive 0.84, those are going to be the boundaries that gets about the middle 60% of that distribution. Okay. Remember, we went through and talked about in our box plots the middle 50, right? Look for the middle 50% of stuff. What's the z-score? What would be upper and lower bound of middle 50? .67, 0.68, somewhere around there, right? So again, using this table flexibly to start going through and grabbing different proportions of the graph there, okay? So questions on how we're using this to go through and find specific z-scores that are corresponding to certain probabilities within this table. You good? Where are we at in terms of? Oh, look at that, my internal clock is beautiful, right? Let's go through, take a 10-minute break, and we'll come back and jump back in and finish up here. Cool. Questions on anything we've done up to this point? Feeling okay about this? Okay, cool. So when we're working with unit normal table, we can move back and forth between probabilities, z-scores, raw scores. So we can go back and forth directly between z-scores and raw scores, back and forth between probabilities and z-scores. We want to go to raw scores, probability. Our z-scores are intermediary. This is what anytime we're trying to figure out a probability of a raw score, what we need to do is we need to take that score, transform it into a z-score, and then we can go through and work back and forth, okay? So again, a lot of different ways that you can go through and pull things apart, but this is kind of the general model that we'll be using for your set 3 as you're going through and working on stuff, okay? So, if we're thinking about probabilities of our individual specific X values, generally what we're looking for and what we're interested in is looking at sort of what's the likelihood of obtaining a score at or above this certain level, right? I'm working in an experimental setting. What's the likelihood of me getting someone with a characteristic of this level or higher if we're assuming this trait occurs on a normal scale, right? So if I've got normative values for a measure, I can actually literally go through and say what's the probability of someone obtaining a score of this level or higher, right? For you clinical folks, this is something that's hugely underutilized, right? We say, oh, well, they just got a score of this on this measure. That means nothing to me if it's in a report. But if you could say tell me the likelihood or probability of someone obtaining a score of this level or higher on a measure of depression, eating pathology, ADHD, anything like that, all of a sudden that means something to me now, right? It tells me how severe relative to a normal population someone coming in with this score is, right? So we start to get some severity. So what we're going to do when we're working with this, we're going to take our raw scores, transform it into a z-score, and then use our unit normal table to go through and look up corresponding proportions. Okay, so if I've got an IQ score forming a normal distribution, mean 100, standard deviation of 15, probability of randomly selecting an individual with an IQ score less than 130. Okay, so I don't know that. I mean, so this actually works itself out fairly easily, right? But if with a mean of 100, standard deviation of 15, what's a z-score corresponding to an IQ score of 130? 2, right? So I've got a z equals 2.0, right? And here, what I'm wanting to know is the probability of randomly selecting an individual with a score of, with IQ score less than 130. What portion of this distribution am I looking at? The left side, right? So if this is 2, I'm looking at all this, right? So already, what do I know my probability needs to be with this? It's going to be bigger or less than 0.5? Bigger than 0.5. Amanda, do you have a probability there? What is it? 977? Okay. Almost a certainty, right? About 98% if I randomly select someone out of the world, 98% of people are going to have a score, IQ score of 130 or less. Okay. This is one thing that starts to get into some of the theoretical math. People say, well, does it make a difference if I'm saying less than a score of 130 or a score equal to or less than 130? Functionally, it doesn't matter, right? Because if we had infinite precision in terms of identify or measuring IQ, the likelihood of getting a score of exactly 130 is 0, right? So we're always looking at sort of the limit before and below. So just don't get too turned around with that. Okay. So another question. If we're looking at trying to find a probability of finding a score between 2 values. Okay. The Highway Department conducted a study measuring driving speeds on a local highway. Observed speed of 59 and a standard deviation of 10. Distribution of speeds was approximately normal. What proportion of cars were traveling between 55 and 65 miles an hour? What do we need to do here? What do we always do first? Graphing this, right? Okay. And so we know here that the mean is 59. And we're wanting to find the proportion of drivers that are traveling between 55 and 65 miles an hour. Right? So we're looking at something coming from here and maybe something going to here. And so this is what we're looking at. So this is 55 and this is 65. Okay. What do we need to do first, Ola?
Calculate the z-score.
Calculate z-score. Okay. So what's my z-score of 55? What's 55 in terms of what's my z-score there?
0.655.
0.655. And what about 65?
0.726.
What is it?
0.726.
0.726? Anybody checking Emilio's math? Are we good on this? Yeah, no, that doesn't seem.
Yeah, that's not right.
Okay.
Yeah.
Yeah.
Okay, good. There we go. So 55z is going to be equal to negative what?
0.4.
Point what?
4.
0.4? Okay. And 65? 0.6. Okay, that seems better.
Yeah.
All right. So how are we going to determine the probability or the proportion of vehicles traveling between 55 and 65 miles an hour? Mean to z, cool. So for 55, so 0.4, what do we get?
0.155.
0.155, okay. And what about 65, or a z of 0.6? 0.226. Is Amanda right? Is that what other people are getting? Cool. All right. Evelyn, what happens if we add 0.155 and 0.226? 0.381. Okay. So we're saying, based on this information, we're saying about 38% of drivers are expected to be driving somewhere between 55 miles an hour and 65 miles an hour. Okay. So again, just using this z-score to go through and say, all right, well, we've got one speed that's falling below the speed limit, or the average, one speed that's falling above. We can go through, assuming that the distribution of driver speeds is following a normal curve. We can use this information to go through and extract how many, what proportion is going on in the middle, even if it's not symmetrical, right? If we're saying sort of the middle 40%, then that's easy to find. Here we're saying we've got different different speeds that are falling sort of at kind of different z-scores. We can still go down through and say what proportion of people are going to be falling within this body of this of the distribution. Yeah.
You may just explain this, but
Yeah.
what's the difference between calculating the middle 50% versus calculating the mean to z for this? Because it looks pretty, I mean, it's not 50% specifically,
Mhm.
but when I was conceptualizing how to get the answer for this, I was thinking I need to figure out what the upper and lower.
Okay. Well, we already know what the upper and lower limit are, right? Lower limit is going to be the speed, whatever z-score corresponds to 55 miles an hour. Upper speed limit, upper limit is going to be whatever z-score corresponds to 65, right? And so if we go through, given a mean of 59, standard deviation of 10, we know 55 corresponds to a z of negative 0.4, z 65 of 0.6. And so we're not getting like the exact symmetrical center. We're higher above the mean than we are below the mean. But if we go through and we say, all right, what's the proportion of the area under the curve, or the proportion of the distribution that falls between -4 and the mean, right? Then we get that proportion, and then we get the proportion that falls from 0.6 to the mean, and get that, and those two together are going to give us that center portion that we're looking for. So if we're looking at middle 50, then we've got an equal distribution. Then we'll have to find one z-score. Here, we're getting from the problem the lower and the upper. Other questions? All right, cool. And so we could do the same thing. We could look at proportion of cars driving between 65 and 75. All right, where do these two values fall, Laura?
I guess with a specific number, just roughly on the distribution.
Or just relative to the mean?
It falls about 2-3 distributions.
Yeah, well, so these are all going to be above the mean, right? And so now this is a little bit different question, right? So here, if I've got my distribution, right? If my mean is 59, and I'm looking at 65 to 75, now I'm looking at this, right? And this is a little bit different. Someone tell me how I'm going to find this proportion here.
You're going to find the z-score, then the corresponding proportion for each, then you're going to subtract the small one from the large
We
one.
use some subtraction, right? I find a z-score for 75, a z-score for 65. Someone help me out. Let's do this real quick.
1.6 is for 75.
Okay, so this is 1.6. And what's
This is for 65 of 0.6.
0.6? Okay, right? So, what is, are the proportion of, or what's the proportion of the curve that going from my midline to 75? So, middle to 1.6.
0.445.
0.445? Okay, cool. So this gives me middle to 1.6, but is that what I want? Nope, right? What do I have to subtract from that? With Emilio?
What was the question? Sorry.
Okay, so we've got 44.5% of the distribution falls between the mean and a z-score of 1.6. Well, we don't want that, right? How do we get this piece right here?
You're going to find the proportion that falls between the mean and the other one. So
And 0.6. So what proportion falls between the mean and 0.6? .26. Okay,
226.
.226. There we go. Okay, so if I take .445 minus .226, what do I get? What's that? 2.9?
219.
219. Bunch of whisperers in here, guys. Shout it, be proud of your answers. .219. Okay, so see what we did here is we just used a little bit of logic, right? So we say, well, we can't directly find this middle piece, right? Because we've got two values that are both above the mean, right? But what we can do is we can say, well, here's the z-score for this, here's the z-score for that. First thing you're going to do with these problems, always graph them out. Second thing you're going to do is find the z-scores for all the sort of markers that you're going to go through and do, and then say, okay, well, I can calculate how much, what area under the curve runs from the mean to a z-score of 1.6, but then I can go through and subtract sort of this middle piece here, and what I'm left with is right here in the middle. Okay. Yeah.
I guess I know the answer to this, but you're not going to penalize us if we use a calculation for the full proportion. Like I use .945 and 726, which is just the full proportion. That's
Yeah, you could use the whole, sort of the larger tail too. It's going to give you the same number. This z table is kind of nice because it gives you midline out to whatever thing it is, but you could do this in a couple other ways too. So people see how it kind of worked through this problem here. Feeling comfortable with this? Okay, cool. I'm going to tell you this is what's going to happen. You're going to forget it. You're going to finish up problem set 2 and then have to jump back into it in problem set 3, and you're going to be confused and frustrated, but that's fine. Just go back through, take a look. It should come to you pretty quickly with this stuff. Okay? All right. We could go through this. So SAT scores for normal distribution. What's the minimum score necessary to be in the top 15% of the distribution? Same thing, we're just going to go through, we're going to calculate, find a z-score here, right? That's going to separate the top 0.5, right? We're going to see what z-score that is, and then we're just going to work backwards. What's the z-score that grabs the top 15% of our distribution? Anything else, Leah?
1.03.
1.03? All right. So what's the z-score that gets the top 15% of the distribution? 1.03? Okay, cool. Just want to make sure. 1.03. There we go. Okay. Now, how do we go through and find the SAT score that's going to correspond to a z of 1.03? What's that?
Would you just set up the equation?
We can set up the equation, yeah. So we would go z equals x minus mean over standard deviation, right? And so we can say 1.03 equals x minus 500 over 100, right? So multiply by 100, right? So this gives us 103 equals x minus 500, right? We add 500 there, 500 here. It's 603, right? And that makes some sense, right? Because we've got a score that's above our mean, right? Just a little over 1 standard deviation above our mean, right? All we're doing here is we're taking our standard deviation, multiplying it by our z-score. That gives us the number of actual units that we're working with this stuff. Same type of thing, we do the same thing for the range of values that define the middle 80% of SAT scores. Again, we can go through, and here we go, Layla, this is where we're dividing, finding the middle 80%. So what's the z-scores that are going to capture the middle 80% of our distribution?
1.28.
Yeah, probably 1.28, right? And so then we're going to take plus or minus 1.28, right? And take those z-scores back translate those into SAT scores, that's gonna give me the SAT scores that are gonna capture the middle 80% of the distribution, where we're saying 80% of people are gonna fall between an SAT score of this and this, okay? Using the same procedure, does anyone wanna work through that one, or you kinda get the idea of how some of these are going?
We would just do it twice, one for the positive.
Well, yeah, because what we're gonna have to do here is we're gonna add a standard deviation and subtract a standard deviation, right? As you said, what do you say, the values 1.28, right? So we're gonna have to take 1.28 standard deviations above 500 and 2 standard deviations, 2 standard deviations below. So basically, because our standard deviation is a nice 100 number, right? We're going plus or minus 128, right? So we take 500 minus 128 plus 628, right? That's going to be our upper and lower limits on this. You see how we did that? All right, cool. So the question is why do all this stuff? Why is this interesting, or anything outside of a cute parlor trick, or sort of something for me to give you busy work to do, so that you're not screwing around. Issue is, and I had said this before, that all of our inferential statistics are based on the assumption of some known distribution, right? Whether it's now we're talking about t distributions, f distribution, chi-square distributions, you recognize these as statistics, but these are statistics because they correspond to some known probability or some known distribution. And if we know mathematically what that the hypothetical distribution is, we can then anticipate the likelihood characteristics of that known distribution. So if I say that if I take the mean of one sample divided by the mean of other sample and divided by the standard error, and I know that the sampling distribution of that statistic follows this distribution, then cool. All of a sudden I can go through and tell you the probability of obtaining a score of this level or higher, and we can start to use that to run some inferential statistics to tell us, assuming that the null hypothesis is true, assuming that there is no difference between these two groups, how likely would is it that I should get a test statistic that corresponds to this amount of difference or more, right? If that's not very likely, then that's evidence within our framework that we interpret that as evidence against the null hypothesis, or and if it is something that's relatively common or not unlikely, then we say that we don't have sufficient evidence to say that so the difference between these two groups are deviating by something greater than we might expect by chance. Okay? And so being able to go through and understand that when we're working with test statistics and we're working with distributions, these distributions correspond to specific frequencies. This is just to kind of help you all sink in this idea that sort of this is kind of the mathematical foundation for our inferential statistics. This is why and how the things we do are working the way they do. Okay. Questions about z-scores using z-tables or finding areas under the curve, things along those lines? Cool. Okay. I'm going to switch gears. So to this point, what we've been talking about is, when we're talking about means and things along these lines, calculating these descriptive statistics as our estimates of our population parameters, right? So I go through, I collect a sample of height of students walking around on campus, and I got a pretty good sample, right? Let's say I gather up 300 kids that I just catch walking around campus, measure their height, and I say, this is my mean, this is my estimator of, if I were to measure the height of all students on campus, this is what their average height would be. I've got a sample of 300. Is my estimate going to be pretty good? What do we think? Sample of 300, am I going to have a pretty good estimate? Probably going to be a pretty good estimate. By the time we get samples of 300, we're getting pretty stable, right? Is it going to be perfect though? No, right? There's going to be some variability. What would be nice to know is the level of precision of our estimates, right? Because what we're doing is we're recognizing this point estimate. The estimate that we get for the mean value of anything in any of our studies That's just our best guess. It's a best guess that's based on the data that we have available to us, but it would be foolish to think that that is the actual population parameter, right? We know that we've measured this with some level of error, right? And so even though our point estimate is our best guess, so we would like to know about, sort of based on our sampling characteristics and some of the stuff that we've done, how much confidence can I have that sort of I've done a good job of measuring some of this stuff, okay? And so how we would approach this is our interval estimation, okay? Interval estimation is giving us both our point estimate, and then what we're doing is we're getting an index of the precision of our estimate, and this is important, giving us some sense of other plausible values outside of our point estimate that we could guess may be reasonable based on the data available, okay? So I'm saying, I've gone through and I've said the average height of students on campus is this based on my sample of 300 people. Well, what would be nice is if I could communicate to you sort of the level of precision that, based on the data that I've had, that I've collected, so this is my best guess. But what other values are reasonable guesses for the true population estimate based on the data that I've collected? Now you see that I've underlined an asterisk this, right? Why, Haley, any idea why I might have underlined an asterisk this?
Because you're still just estimating based on what you collected, not the actual population.
Right. If my sample's garbage, who knows whether or not I've got a reasonable estimate or not, right? So again, this gets back into our methods, right? Our statistics, our inferences are only as good as our data. And if our methods are shoddy, it's really hard to tell where we're at with stuff. But assuming that we've done our due diligence, got a reasonable sample, right? What we can do with our interval estimates is say, okay, here's my best guess, but here's some reasonable values that might fall within that, right? So again, if we say, research suggests that people who exercise 5 hours or more a week live longer than the average US citizen, right? Question might be, well, how much longer do people live, right? Well, I can say, well, this amount maybe, but it could be anywhere from this to this, right? That starts to give me a little bit more information. It gives me a stronger interpretation of this study than just saying, well, people who exercise 5 or more hours a week live 3 years longer. Is it exactly 3 years longer? Well, probably not. There's probably some variability, right? If I start to give an interval estimate, it tells me kind of the precision of that estimate, right? We can say height between men and women is not 0, right? Well, that's good, right? But this is what we get in a lot of our statistical tests, right? We say, well, men and women are different in height. Good to know, but I already knew that, right? What might be interesting is to know, on average, sort of what's our best guess at the difference, and then sort of based on our estimate, how close are we, or how much precision do we have here, okay? So this is where our confidence intervals come into play, right? Confidence interval is our interval estimate based on a certain level of precision. For calculating confidence intervals, we're going to have our point estimate, okay? This is our best guess, right? This is our average or our mean if we're talking about confidence intervals around mean. This is our best guess that we've calculated. But then we're also going to say specify a level of confidence, and then we're going to have our interval estimate, right? This is giving me an upper and lower bound for the range of plausible values for my true population parameter. Okay? Because I know if I go through and I calculate anything in any study that I run, all right, and here's the mean value. Nick, if I had to say, tell me how certain you are that this is the actual real value, like this is the actual population parameter, what should your estimate be?
Sorry, can you repeat?
Yeah. So I say, so you're studying, and what's your area of research, Nick?
Jury research.
Jury research. All right. So let's say this is the average age of jurors or something like that. Okay, and you get average age is 30.5. That doesn't actually make sense, but let's pretend it does, right? And what if I were to say how confident are you that the actual population, the mean age of jurors in the U.S. population is exactly 30.5? What should your answer be?
0, you can't be 100%.
Exactly. 0. It's never going to be exactly 30.5, right? It's going to be something different, right? But the question is how confident. So if I know it's not that, right? What are the ranges that this could be, right? How precise are my estimates? What if I said, okay, well, it's not 30.5, let's say, but it's 32. Is that reasonable? Probably. If I say, if this is my estimate and I've done a good job of sampling, and I say, oh, the true estimate is 50, that's probably not going to be reasonable, right? So it's just giving us an upper and lower value again. But if you had to put my foot to the fire, I'm going to say 30.5, and I'm going to be less wrong than any other guess I could make based on my data. But we want to have this interval estimate, right? So formal interpretation of our confidence intervals, right? From an actual sort of theoretical standpoint, what we're saying is over an infinite number of replications, right? What we would say is this is giving us the proportion of intervals expected to capture the true population value, right? So let's say I sample 8 juror ages, right? And I have samples of 100, right? And so I collect 1,000 replications, so 1,000 samples of 100, and I collect the mean calculated confidence interval for each of those 1,000 samples, right? What I would expect, based if I'm calculating a 95% confidence interval, I would say that 95% of those confidence intervals capture the actual true population age or mean age of jurors, right? So I'm going to have 5% of those intervals over the 1,000 that I've created. 5% of those are going to have an interval that doesn't include the population estimate or the population value, but the other 95% will calculate it. Okay, and so again, what we've got is technically a frequentist approach to interpreting confidence intervals, right? And so because of this, we would say it's not correct to say, and this is what we hear all the time, right? There's a 95% chance that the confidence interval contains the true population parameter. Okay? Who's heard this interpretation of confidence intervals? Everybody's hand needs to go up, right? This is what we hear. So there's 95% chance that the confidence interval contains the true population parameter. This is technically incorrect. Okay? If we go through and we calculate, so we have some. Let's say this line is the actual population parameter, and this is a hypothetical value. We can't actually know this 99% of the time because we generally aren't able to get. This is the actual population value of heights of student on campus, right? We could probably actually, with enough time and effort, we could actually probably calculate that population value. But let's say it's average age of citizens in the U.S. or residents of the U.S., right? This is some unknowable figure because we're obviously not going to go through and we can't feasibly calculate everybody's age and get the average age of the people residing in the U.S., right? But what we could do with nice nationally representative samples is we could go through and we could calculate and we could gather, say, a sample of 1,000 people, right? And calculate their average age. And then do it again, and then do it again, and then do it again, and again, and again, and again, and again. What our confidence interval is telling us is that if we go through, and this is the true population age, right? Some of our interval estimates, most of our interval estimates, assuming that we've got good methods, are going to capture the true population parameter within that interval, right? But some of them aren't. Sometimes we're going to get interval estimates just for one reason or another that I'm saying that so here's my point estimate and here's the upper and lower bound for plausible values, but in actual fact, that interval estimate missed the actual population value, right? What our confidence level in our confidence interval is telling us is it's giving us the proportion of intervals that are created over the course of an infinite number of replications that are expected to capture that actual population value. Okay? So most of our interval estimates with repeated replication are going to still get that value. Some of them aren't. And so if we go through and we claim that there's a 95% chance that some interval, right, contains a population value, what we're assuming here, what we're implying, is that our population value changes. So I calculate, this is my confidence interval for the average age of people in the US, right? And I say that there's a 95% chance that the true population, the true age of the US residency falls somewhere between 38 and 58, okay? And if I say there's a 95% chance that the true parameter falls between there, it's suggesting that sometimes the population parameter is going to fall between 38 and 58, and sometimes it's not, right? Well, for any one of these intervals, right, the population parameter is either in there or it's not in there, right? For these ones, so what's the likelihood of the population parameter falling within this interval? 100%. Yeah, it just does. What's the likelihood of the population parameter falling in that interval? 0, right? And so when we're making interpretations of our confidence intervals, right, we're making a statement about the process of creating intervals and process of creating estimates, right? So either for any given interval that we capture, either the interval that we've created based on my one study, it either captures the population parameter or it doesn't, right? So to say that there's a 95% chance that this interval captures the population parameter, it's technically not correct because either I've got it or I don't, right? But what I'm saying is over an infinite number of replications, using this method, using this sample, we would expect 95% of interval estimates to have captured the actual population parameter of interest. Is anybody not satisfied by this? You give me side eye, Amanda.
So go back a slide.
Yeah.
So does that mean for your interval estimate, is that saying that between those two, if this is the age thing,
Mm-hmm.
that those are the two bounds under which the population age really lies?
Based on these data, right, what we would say is based on the data that I've collected, right, and what this is sort of assuming my methods, that my best guess for the average age of jurors is 30.5.
Right.
And based on my methods, right, that value could be anywhere from 18 years of age to 43 years of age.
Those are kind of your upper and lower bounds.
The upper and lower limits based on the data that I've collected.
And your 95%, you have a 95% confidence.
And this is what I'm telling you right now. This confidence level, this 95, that's part of the calculation. Kick that out.
Okay.
Okay? You'll tell me I calculated a 95 confidence interval. That tells me sort of the confidence level that you're getting out. What this is technically saying is that given sort of my method, I would expect that 95% of the intervals that could be counted over an infinite number of replications of this sampling would actually capture my hypothetical population value. But I don't know if this one does, right? Either this interval that I've created, either it does or it doesn't. But I don't know, right? And this is the rub, right? When we're going through and we're calculating our study, I don't know if my study is one of these ones or if my study is one of those ones, right? There's no way for me to know, right? So I can't say that there's a 95% chance that this interval captures the population parameter, right? Because that suggests that population parameter is a variable, that it's jumping around. Population parameter is population parameter, it's a constant, it's a value. My interval actually either captures it or doesn't. Fortunately, I don't know whether my interval captures it or it doesn't capture it, right? What I'm saying is there's a potential that my interval estimate that I've calculated might be one of these ones. It might be that 5% that misses it completely, right? So not a likely chance, but it's certainly possible, and I don't know, okay? This is where meta-analysis starts to come into play, right? And this is where this starts to become such a valuable, and so the growth of meta-analysis starts to become important, because then, if there's lots of studies that have looked at the same thing that I have, right? I can start to get a plot like this and see whether or not my estimates are way out of bounds or whether or not they're falling within things that people are typically finding, okay? Now, you should know based on your own understanding of your research area whether or not yours is a reasonable value or not, right? But wanted to be very specific in terms of we're thinking about what confidence intervals mean and what they don't mean. And the problem with saying that there's a 95% chance that true value in the population falls between X and Y, well, not really, because either it's 100 or 0. You've got two options, right? Because our interval estimation is about the process over an infinite number of replications. If we did this over and over and over and over again, our confidence level tells us how many of those interval estimates that could be calculated would actually capture the parameter of interest. Okay? Yeah.
So then basically we would just be saying like our best guess is the mean, but like our best guess could fall anywhere between like
Yeah.
18 or 43.
Based on the data that we've collected, right? And so you're standing next to your data, right? Now, if you know your data are garbage, then, right? But we're saying, this is my best guess, and this, based on the data that I've collected, these are the upper lower limits, right? And so what I'm gonna encourage you to do when we're thinking about conceptually, thinking about confidence intervals, right? So this infinite number of applications, know that as a technical term, but erase it as an interpretive thing, right? Because if you get into a paper and start talking about infinite number of applications, reviewers' eyes are gonna go crossed and they're not gonna follow you, right? In a frequentist approach, when we're thinking about what we're doing with intervals, the process of creating intervals is talking about over replications, how many of those intervals are expected to actually capture the population parameter. But if we're talking about intervals, right, there are some different ways we can communicate this more appropriately and accurately than saying there's a 95% chance that my interval captures the population parameter, okay? So you might say confidence interval represents a range of plausible values for a parameter given the available data. Range of plausible values for whatever it is that I'm trying to measure, ranging somewhere from this is the lower estimate to this is the upper estimate, okay? And sort of the corollary of this, values falling outside of my interval are relatively implausible. Right? Not saying they're impossible, right? It's just saying that they're probably not likely based on the data that we've collected. This is a wonderful conceptual interpretation. Notice I haven't said anything about any level of confidence here, right? Level of confidence is something that goes in computation, right? And if my confidence is making it a 95% confidence interval, 99% confidence interval gets smaller, 90%, or excuse me, bigger, 90% confidence interval gets smaller, right? We're not worried about level of confidence here because you've told me what kind of confidence interval you've got, then you're making a conceptual interpretation. Another way you might describe your confidence interval, say observed data are compatible with values over a parameter falling within the interval, but relatively incompatible with the values falling outside the interval, right? So if I have a confidence interval that runs from 20 to 25, right, and I say my point estimate is 22 and a half, and Haley, you say, well, I think it's probably more like 24. Like, okay, fair enough, right? It's not my guess. I wouldn't guess that. I would guess 22.5 because that's what I got, right? But 24, I can see 24, right? Based on my level of precision, 24 is plausible, right? But Nick says it's 15. I was like, well, probably not, right? Based on the data that I've gotten, that seems inconsistent with the data that I've gathered, right? So we like this one. We can also interpret this as a lower limit of the interval provides a reasonable lower bound estimate of the parameter, upper limit, reasonable upper bound of these data, right? And this starts to get into making you think more about what we've measured, right? Here's what I think the value is based on my best guess. But sort of here's a reasonable lower limit for what that parameter might be. Here's a reasonable upper limit based on the data that we've collected. Okay? That would be nice. Other one way you could think about this, talking about the margin of error. Okay, your margin of error is kind of that plus or minus. Here's the mean plus or minus 5, right? In your confidence interval, you calculate that. So the margin of error reflects the largest error of estimation likely to be made based on these data, right? So here's my point estimate, but margin of error largest margin of error we would expect based on these data is 5 points, 5 points plus or minus. Right? We can be 95% confident that our interval includes the mean. Just scratch that out. I don't want to hear that. Okay. And again, please don't tell me anything. If I'm asking you for an interpretation of your confidence intervals, unless I'm asking for a technical interpretation, please don't tell me over an infinite number of replications, 95% of the intervals that could be calculated would capture or are expected to capture the actual population parameter. That's technically right, but it's not going to be an effective way to communicate anything to people, right? If I'm running IQ tests, right? If I'm running an assessment and I put Angeline's IQ at 120, you comfortable with 120? Okay, right. And I say that it could be anywhere from 115 to 125, right? If I'm communicating this to Angeline's parents, right, I'm saying, well, over an infinite number of replications, you're going to lose them, right? But if you say, so based on this evaluation that we've given your daughter, this is our best guess for kind of where this is at, but really any place from 125 to 115 is going to be reasonable estimates given sort of the level of precision of this exam, right? That means something. People say, okay, well, this is kind of, but there could be above and beyond, right? And so what I want you to start doing is use these, sort of interchange these, right? Depending on what you're talking about. What I don't want you to have is a stock language that you drop into anything that you're not thinking about. You're just dropping it, because it's not helping you understand and utilize these correctly. Think about, given what you're doing, what you're studying, how you've gone through and calculated it, and saying, okay, is this, sort of what does this mean, right? Because this starts to become important, right? If I'm talking about how many extra years I live if I exercise 5 hours a week, boy, it could be anywhere from, my best guess is, say, an extra 3 years, but it could be anywhere from half a year to 7 years. Like, oh, wow, okay. So that tells me something, right? Or if I'm predicting some outcome, right? And like, well, so this is my point estimate, but it could be anywhere from, and my point estimate is 25, but it could be anywhere from 2 to 80. That tells me I'm not very precise in my estimate, right? So utilizing these, thinking what these confidence intervals mean, playing around with different ways of talking about those, are going to help solidify this, sink this in, so you can start using this these interval estimates effectively. Okay. And so again, Cohen talks about one of these articles. Researcher who routinely reports 95 confidence intervals can expect that over their lifetime, about 95% of those intervals will capture the parameters of interest. Right? I mean, again, if we're just doing it again and again and again and again, the confidence level is telling us what proportion over replications are expected to capture the population parameter. Confidence isn't telling us anything about sort of this specific thing, right? And so you'll notice here that we're not talking about levels of confidence in any of these interpretations. We said, I calculated a 95% confidence interval. You've communicated to me the procedure that you've used to calculate this interval estimate. Then you can go through and proceed to give a reasonable interpretation that doesn't have to involve level of confidence. Angeline, anything that you would add to this? This ends up being a very tricky thing, and people are having a hard time getting a handle on this. We'll provide instructive feedback on sort of your interpretations, but this is something, again, if you think back to that Wilkinson, some of those articles I had you write up, right? They're saying, like, you should always be reporting confidence intervals with stuff. We don't, but I'm going to make you, so hopefully it becomes kind of like a reflex reaction, so then when you're actually doing your own research, that you are reporting these, because it's taken a while to get this ship turned around, right? Angeline, anything that sort of you can think of that helps sort of solidify some of this?
I think what helps solidify it in the long run for me is writing them in different ways, so it'll be really easy to have like a formula that you follow to write interps for confidence intervals, and then like I found myself not understanding what I was actually saying sometimes if I did that. So just like making sure you understand what you're actually writing on paper, and then like maybe talking them out and like what confidence intervals mean. I'm happy to do that with people if they want, because I know the interps got a little tricky for me in my cohort. but I think practice makes perfect with
Yeah.
dealing with confidence intervals.
And it's a different way to think about things, right? But it's a much more accurate way to approach our statistical inference than just saying, here's the mean of my sample. Because again, I don't care about my sample. My sample is only a device to get at some value in an intended population, right? And so we know that my value of my sample, the probability of that being exact is 0. So what are the, based on the data that I've collected, what are sort of maybe the upper lower limits of this actual parameter of interest?
So, just
Yeah.
to think about it in a different way for me, so if I had a confidence interval of 50%, I would essentially be saying that my upper and lower bounds might contain the actual value about half of the time.
No. Okay. So again, that's kind of getting back to sort of this thing, right? What that would say, if I'm calculating 50% confidence interval, so let's say I'm interested in the average increase in sales due to advertising, okay? And I say that I'm saying it's a 30% increase in sales. Based on the data that I've collected, that's my point estimate, right? But if I calculate a 50% confidence interval, right, that's saying if I did this study again and again and again and again and again and again, the confidence intervals that I would create with each one of those studies, half of them are going to miss the true amount that this advertising campaign increases your sales.
Okay.
And that's not going to be acceptable, right? And so generally, our confidence intervals often are typically mapped back onto our acceptable level of type 1 error, with some exceptions. So generally, we're talking about 90% confidence intervals, 95 and 99% confidence intervals, right? And so then if I go through and I calculate a 99% confidence interval for that study, I'm saying, if I were to do this study again and again and again and again and again, 99% of the hypothetical intervals that would be estimated within that across those studies, 99% of those would capture the population parameter of interest, right? And 1% wouldn't, right? So again, I would worry less about sort of the confidence level because that's already kind of predetermined, and worry more about sort of stating sort of the type of confidence interval that you created, and then sort of making interpretations from that. Angela?
Yeah, I mean, I think I was just gonna say exactly what you just did, but I think my cohort and I got really hung up on the 99 and 95 and like the actual percentage in front of the confidence interval, and that's really not what it's about. Well, it is part of it, it's not what it's about in your interpretation or your understanding of
Yeah.
them. So try to
Try and divorce. And then again, play around with some of these and try and talk about it different. And so with anything else, right, as we're working through this stuff, if you sit down and say, literally, what does this mean? Right? Very, very, in a literal sense, what are these numbers telling me? Well, it's saying that based on the data that I've collected, this is sort of my best guess for the average of whatever it is that I'm collecting. But this interval estimate is saying that true value could be anywhere from here to here in terms of a range of plausible values for this, or this is an upper limit, or this is a lower limit, or values that fall within this interval are plausible. Things that fall outside are not consistent with the data that we've collected, right? Thinking about different ways to go through and talk about this, and as you do that differently and think about it, you start to solidify on this. Yeah.
I also always thought to use the alpha when describing the confidence intervals. Is that something you would say you do? Or
Do you use the what?
the alphas? Like alpha 0.05 or...
I mean, if you just say I've calculated 95% confidence interval, I
That's the
understand
same.
kind of what's going on with that. Yeah. All right. So strengths of our interval estimation. Okay, gives us a point estimate. Okay, this is going to be our best guess, and probably most important, an estimate of probable error in our prediction. Right. We tend to just throw out point estimates and just say, oh, yep, this is sort of my guess. Well, my guess might be really crappy. What's the biggest thing that determines how good our guess is? Yeah.
Is it the study design?
Study design is probably up there, but in terms of the functionally calculating our confidence interval, what gives us really small confidence intervals?
Small samples.
Large samples.
Oh, sorry.
Large samples, right? As our sample size starts to increase, we're expecting less and less measurement error, right? And so our precision often is determined most strongly by the sample size, but our study methods do as well, right? But that's often not captured within, there's no correction for study quality when we're calculating our confidence intervals, but as our sample size starts to get larger, our confidence interval starts to shrink. So again, our interval estimate emphasizes how much, which is generally more useful than is it equal to 0, which is what our hypothesis test is almost always doing. Is this value different than 0? Is the difference between group and A 0? Yep. Okay, well, good to know how much, right? Interval estimates start to tell us more about that, okay? Also, our confidence intervals give us identical information to our significance tests, okay? If our 95% confidence interval contains some reference value, this is interpreted as evidence in support of our null effect, right? If I'm saying the difference is 0, and the confidence interval for my difference is 0, runs from -2 to +5, it's saying that 0 is a plausible value because 0 falls in my interval estimate, right? And so I would fail to reject the null hypothesis in that situation, right? Because 0 is kind of right in the middle there, right? So I don't need to go through, actually, technically you don't need to go through and run my hypothesis test because I already know what the answer is going to be, right? But if, say, my null hypothesis is that the difference between group A and group B is 0, and my confidence interval for the estimated expected difference of the between these groups runs from 2 to 8, right? I can reject the null hypothesis. I already know I'm going to reject the null hypothesis because 0 is not a plausible value. 0 is not my estimate. A difference of 0 between these two groups isn't in there. So I know that my null hypothesis is inconsistent with the data that I've collected, right? And so the only thing that we get from a significance test that we don't get from an interval estimate is a p-value. Okay? And as we'll talk, sort of limitations about p-values, that's not necessarily a terrible thing. Okay? And then it's going to provide more accurate, meaningful perspective on observed effects in the literature. This is where our meta-analysis starts to come into play, right? For my individual study, right? For all the work and effort that goes into running my individual study, does my individual study tell me a whole lot about anything? Probably not, right? Because who knows where my study falls. My study could be that study, and I have no knowledge, and I have no way to know whether or not my study is one of these or one of these, right? For you experimental folks, sort of this whole replication sort of situation, people get real bent out of shape about that, right? And it's a crisis, a replication crisis. Well, not if you understand basic statistics, it's almost guaranteed, right? Like no one should have been shocked that that was a thing, right? That someone found a weird effect that is really quirky, and then one person found it and published it, and then no one else could replicate that. Well, that's because someone published that, and that was interesting, right? But we're never gonna, it's a hard time replicating that because the actual population value is down here, right? This is 0, this is null, this is one study that found this. Like if you understand basic statistics, no one should be shocked that there's a replication issue, particularly given how we go about conducting our statistics and publications and things like that, right? And so this is where our meta-analyses start to come into play. If I've done a study, and Amanda's done a study, and Kate's done a study, Haley's done a study, and we all start to find that sort of all of our studies are kind of in the same ballpark, and Emilio's study is way out of bounds, well, either something went wrong or just a bad luck of a draw or something like that, right? We can start to get closer and get a better sense of what our actual parameters are going to be, okay? So from our Wilkinson article, inclusion of confidence intervals for estimates of parameter, functional parameters such as differences in means and effect sizes, extremely effective way of reporting results. Confidence intervals combine information about location and precision, in general the best reporting strategy, okay? Now this is confusing because how often do we see confidence intervals in our publications? Not often, right? Why not? Any ideas?
Because a lot of times it takes up more space.
It takes up more space, but it doesn't have to, right? And it actually gives us more information than we would just using some other things, right? My hypothesis, one, it's an instruction issue, right? We go over hypotheses in undergrad statistics and then forget about it and don't ever talk about them, right? Two, they're not required. And so if they're not required, why would I learn to sort of use these flexibly if I don't have to have them in there? But then three, how precise are our estimates in our psychological studies? Not very, right? And what you'll find when we're calculating our confidence intervals for things, oftentimes I've got my confidence interval says the true difference between these two groups ranges anywhere from 1 to 20, right? Boy, it's just a lot nicer if I can just say, yep, they're statistically different, and then leave it at that, right? But if I provide that confidence interval, what I'm saying is like, yeah, they're different, but just barely. And the difference could be between these the true population means could be anywhere from 1 to 20. I don't know, I feel less good about that, right? Again, I'm claiming, I can claim statistical significance because my interval estimate doesn't contain 0. It also runs from 1 to 20, which makes my study looks less good, right? If I'm saying this is the level of uncertainty based on this study, right? Our confidence intervals can sometimes make us uncomfortable, right? But I think that's an important thing to know, right? That level of precision or imprecision is an important factor in determining sort of the confidence that I can place in these results, right? And so if I go through and I run a replication and you said, well, I found an average difference of 10 points, but my confidence interval says I could have a difference. That makes me feel better because even though you found sort of a difference of 10 points, your interval estimate says that my difference of 2 isn't really all that. It's not outside the range of what you would expect based on the data that you collected, right? Okay, there's a lot of sort of soapbox stuff about confidence intervals, but questions to this point? All right, I'm gonna be looking for this, all right? If you're running statistical tests, I'm gonna be looking for a confidence interval. If you haven't provided confidence interval on something, this should trigger warnings in your head that, oh, whoops, I should be doing something here and making sure that I'm calculating this stuff and making interpretations, okay? All right, if we're calculating confidence intervals, 3 pieces of information. If we're calculating confidence intervals around means, we've got a sample mean, we've got a standard error, and then some test statistic that's chosen based on our select degree of precision. Okay? So we know what a sample mean is, right? We've got that. Standard error, we're going to talk about standard error a little bit more, a lot more. It's going to come up again and again and again throughout the course of the year. We're going to talk about standard error a whole lot, right? But in general, for right now, thinking about your standard error as an index of how much error difference is expected from one replication sample to the next, okay? So if I run this study today and I run it tomorrow and I run it the next day, how much am I expecting this mean to jump around across these studies, right? So do we want big standard errors or small standard errors? Small standard errors, right? We want our stuff to be more consistent, right? In general, our standard errors are telling us how well our individual sample mean is expected to estimate the actual population mean. Calculation of standard error is going to be our standard deviation divided by the square root of our sample size. Laura, what happens to our standard error as our sample size gets increasingly large?
It's smaller.
It gets smaller, right? Our precision gets better as our sample size gets smaller. This denominator here tells us why sample size is so important for our statistical tests. As that starts to increase, our standard errors get smaller. Our standard errors are almost always what's being inputted in the denominator of our test statistic. If we're putting a smaller number in the denominator of our test statistic, what happens to our test statistic? It gets bigger, right? And we like big test statistics, right? So mathematically, you can see primary influences on standard error is variability in our sample, right? Or population, I guess we're talking about here. So our population standard deviation, but then our sample size as well. And so again, we'll talk again and again and again and again about standard. I'll tell you this, guy, if I ask you a question you don't know the answer, standard error is a good guess. Statistically, it's probably the best guess you can make. Like, I don't know, does something to our standard error, just if you have that in your back pocket, okay? Other thing that we're going to be working on here is using our test statistic that corresponds to the precision of our estimate. Here we're going to be using Z statistics, right? 90% interval corresponds to a Z of 1.65, 95% interval, Z of 1.96, 99, 2.58. Okay. Where am I getting these values from? Yes, Layla, exactly my Z test, and sort of where are these individual, like why is Z of 1.96 associated with 95% confidence?
Associated with
Mm-hmm.
because of the Y value?
Okay, not the Y value. Someone help her out? Yeah, jump.
The smaller portion is 5% of it, so if you do look at like both tails, it's like 10%.
Yeah, right. So 95, if we look at poor portion in the smaller tail, right? We're catching 2.5% in the upper tail, 2.5% in the smaller tail. So 95% confidence interval is getting that piece there in the center. Same thing if we went to 90% confidence interval, right? We're chopping off 5% in the top, 5% in the bottom, right? 1.65 is going to correspond to 5% in the upper and lower tail. Same thing, 2.58, that's going to capture 0.5% in the upper tail, 0.5% in the lower tail. These are good values to just kind of internalize, memorize in your head, because they'll come up again and again and again. 3.29 is 99.9%, or equal to P less than 0.001. So these are the things we're going to be using here. So our confidence interval is our mean plus or minus our test statistic multiplied by our standard error. Okay. So I'm going to finish up with example here. So we've got a former librarian, a local library, is claiming that on average, books in the library are 20 years old. New librarian interested in re-estimating age of the library books, goes through, randomly selects 150 books, records the publication date, right? Mean age of the books in the sample are 23.8 years with a variance of 67.5. Okay. Calculate a point estimate for the true age of the books. Kate, what's our point estimate for the true age of the books here? 23.8. That's our best guess. Do we think the actual population, if we were to gather all the books in the library, record their age, do we think it's going to be actually 23.8? Probably not, right? We're probably going to have some error, but this is our best guess based on the data that we've collected, right? So what I want to do is I want to determine how precise this estimate is, right? So I'm going to calculate a 95% confidence interval. So I've got, mean is 23.8, is that right? Okay. And what's my standard deviation here?
8.22.
8.22. How'd you get 8.22?
Took the variance and
Perfect, right? So we take standard deviation is going to be the square root of 67.5, right? Standard deviation is going to be, what was it? Did you say?
8.22.
8.22. Okay? Threw you a curveball there. You give you a variance instead of standard deviation. You plug variance into stuff, you're going to be way off base. It's too big. Okay? All right. And so I want to calculate 95% confidence interval. So my Z-score here is going to be what? 1.96. What's the last piece of information I need to calculate my confidence interval? My standard error, right? So my standard error here is going to be my standard deviation, 8.22 over the square root of my sample size. How many samples, how many books did I collect? 150. Okay. Someone tell me what my standard error is. What is it? 0.67? That sounds about right. Is that what other people got? Anybody? Yes. Yes, okay, perfect. All right, so we've got all the information we need to calculate our point estimate, right? So my 95% confidence interval is going to be my point estimate, 23.8, plus or minus my test statistic, 1.96, corresponds to a 95% confidence interval, times standard error, 0.67. Okay? So what's my, someone tell me what's 1.96 times 0.67? What is it, Layla?
1.31.
1.31? Is that what other people got? Okay, this is our margin of error, right? When we're talking about greatest margin of error based on our estimate, we're saying that on average, we're expecting our error to be, based on the data that we got, 1.3 years above or below sort of our point estimate. So someone tell me what's my lower bound estimate for this interval here? 23.8 minus 1.31.
22.49.
22 point what?
49.
49?
Yeah.
And what's my upper bound?
25.1.
25.1. Okay. Okay. And now, what I want to do is I want to provide an interpretation of this, right? And so what I'm going to say is my best guess, based on my estimate of actual age of books in this library, is going to be 23.8. That's my best guess, right? But based on the information that I've collected, I'm saying that the true age of books in this library could fall anywhere from 22.5 to 25.1 years of age, okay? Values that fall within this estimate are plausible given my data. Values that fall outside of that are relatively inconsistent with the data that I've collected here, right? I'm not saying it's impossible, but I'm saying it's implausible. Okay? So Emilio, we say a former librarian said that on average books were 20 years old. Does that seem plausible given the data that we've collected? No, why not?
Because it falls outside of the confidence.
20 is not within my interval, right? 20 falls outside, right? So maybe when the old librarian did it, right, maybe that was the age. But today, the value of 20 is not within my interval, and so that seems relatively implausible based on the data that I've collected. Not impossible, but not likely. Okay. Now, formal interpretation of this would say, and I think this is a good example. So here's a library, right? And I randomly selected 150 books. I'm assuming there's more than 150 books in the library. If I were to do this again and again and again and again and again and again and again, going through randomly selecting 150 books, calculating the average age and creating a confidence interval around those that age, I would expect that 95% of the intervals that I would collect with replication would capture the true population age of those books, right? Now, I don't know if this interval itself does, but I wouldn't say that there's a 95% chance that this interval captures the true population age of books, because either it does or it doesn't, right? But what I can say is, based on the data that I've collected, my best guess is to the true age of the books is about 23.8, and sort of lower bound and upper bound estimates range somewhere between 22.5, 21.1. So in general, Nick, how do we feel about this interval estimate here? I mean, if we're thinking about what we're trying to do, we're trying to guess the average age of books, right? And so if we look at this interval estimate, are we satisfied with this interval estimate?
Yeah, because our mean falls with that.
Okay, this is a trick, all right? It wasn't a trick, but I think you felt it. So Nick said, yeah, we're happy with this because the mean falls within the mean that we found falls within our interval estimate. If we've done this correctly, will the mean ever not fall in our interval estimate? No, it won't, right? It always will, right? If you've got a point estimate that falls outside of your confidence interval, something's gone wrong, right? You know by definition you messed something up there, right? If I'm looking at this, right, I've got a margin of error of 1.3 years, right? That's pretty good, right? If I'm trying to guess something like the average age of books, I don't know, books hang out for a long time. If I think about how old some of these books are in libraries, if I'm tolerating an error of 1.3, I'm feeling pretty good about that, right? And so based on what we're trying to collect and what we're trying to do, I'm pretty comfortable with this, right? Now what happens if I said, oh, here's my point estimate, so my average age is 23.8 and the average age of books could be anywhere from 3 years old to 75 years old. Would I be satisfied with that? Probably not. That's a pretty massive range given what we're trying to measure, right? And so I would be less excited in that perspective, or in that respect. Laura, what has gone into making sort of this interval estimate pretty tight and acceptable?
Well, there's a large sample size.
Yeah, that's what it is, right? I've gone through and I've collected a good sampling of books. I've gone through, randomly pulled 150 books off the shelf. That's a pretty decent sized sample, right? And we'll get into more about sort of sample size and how that impacts standard error and things along those lines. This is what's going on, making that standard error fairly small is what is going to go through and impact that margin of error.
So if you get a margin of error that's pretty significant, you might want to rethink what you're doing and pull a bigger sample.
You might, right? It just kind of limits kind of what we're trying to tell people, right? And so if I'm, and this starts to have an impact in the field such as yours in marketing, right? If I'm trying to say, here's, so this is how much your advertising campaign is going to cost, right? And so this is based on our model. I'm saying that this is going to increase your sales by 40%. But based on my margin of error, it could be anywhere from 2% to 150%. I don't know, right? Yikes. Particularly if that marketing campaign is going to cost me a lot of money, I'm not satisfied with that, right? And so something needs to happen with methods and sampling, kind of decrease that down a little bit. Okay? So all of this stuff is things I want you to be thinking of in terms of as you're working through problem sets, when we get into actual data and you're calculating and interpreting these intervals, think about what am I looking at? Is this an acceptable margin of error? How do I interpret this within the framework of the research question at hand, so on and so forth. Okay. So here we go. We do another one there. All right, we'll pick this up next time when we come in. So, all right, questions, folks? All right, cool. So make sure you're getting a head start on